Hello, I am Seema and welcome to part 30 of the chapter Haloalkanes and Haloarenes. We were doing the electrophilic substitution reactions of haloarenes and I explained the different electrophilic substitution reactions in the previous video. We'll move ahead with our discussion of electrophilic substitution reactions. In class 11, you have done the mechanism of electrophilic substitution reactions and this would be a very good time to revise them revise the mechanism because that will help you understand the electrophilic substitution reactions in haloarenes. So let me just recapitulate what we did in the previous video. I told you in the case of chlorination, the reagent that we use chlorine along with AlCl3, that is anhydrous aluminum chloride. Similarly, for methylation and acylation also, we use AlCl3, anhydrous AlCl3, we use it in the reaction. And there is a purpose of that AlCl3. When we were carrying out the nitration, for nitration, we use the nitrating mixture. And the nitrating mixture is a mixture of nitric acid and sulfuric acid. And the third was sulfonation, where you use oleum or concentrated H2SO4 which has been heated, which results in the release of SO3 gas, and therefore the SO3 and concentrated H2SO4 in a way are the reagent that will be used for sulfonation. So let us understand what happens when electrophilic substitution takes place. Electrophilic substitution reaction would take place in 3 steps. When we say electrophilic substitution, it means an electrophile is going to substitute something in the benzene ring. It is going to and what is an electrophile? An electrophile is let us say a species which is positive in charge, and it is attracted to electrons or electro. Electro means negatively charged, phile means phila is love. So electrophilic, it loves negative charge. So what would love negative charge? Positive charge would love negative charge. Therefore, an electrophile is a positively charged species. And the substitution is taking place with the help of an electrophile. Therefore, the first step is generation of that electrophile. In the first step, that positively charged species has to be created, which is going to function as the electrophile. So let us take this example of chlorination. In chlorination, we have chlorine where 2 chlorine atoms are bound by a covalent bond, and we use AlCl3, aluminum chloride, anhydrous AlCl3. Anhydrous AlCl3 acts as a Lewis acid. What is a Lewis acid? What are acids basically? Acids are proton donors, so that is, and they are electron pair acceptors. So in terms of Lewis, we talk in terms of electrons. So a Lewis acid is one that accepts a pair of electrons. So AlCl3 acts as an electron pair acceptor. And what happens in this, the covalent bond between the 2 chlorines, it does not break symmetrically. It breaks unsymmetrically or asymmetrically, where one chlorine gets 2 electrons and one chlorine becomes positively charged. So there is an asymmetrical cleavage of the bond that takes place, leading to both the electrons of the bond going to one atom, and one atom, therefore the other atom becomes positively charged, and the one that gains both the electrons, one was its own and one was the electron of the other chlorine. So it gains 2 electrons of one electron of its own from the covalent bond and 1 electron of the adjacent atom, which is chlorine. Therefore this chlorine would become positively charged and this chlorine would become negatively charged. The negatively charged chlorine will go and it will attach itself to aluminum. Since it has got the 2 electrons, it uses those 2 electrons, 1 electron which is its own and 1 electron which it took from chlorine, and it uses those to form AlCl4 anion, right? AlCl4 negative is formed, and the Cl positive that is generated, that positively charged ion is known as the chloronium ion. And since it is positively charged, this would act as an electrophile, right? In the case of Friedel-Crafts alkylation and acylation, we again use AlCl3, and AlCl3 is doing the same job here. In the case of Cl2, the asymmetrical cleavage was taking place between the 2 chlorines, but here the asymmetrical cleavage is going to take place between carbon and chlorine. Actually, this is easier. because chlorine is more electronegative than carbon, and therefore it as it is has a tendency to pull the electrons towards itself. So this cleavage would be easy. You will do it in the presence of AlCl3 to facilitate, to help, to make sure that the cleavage is asymmetrical. And the same thing happens this time. The cleavage is asymmetrical. Chlorine, being more electronegative, picks the electrons, pulls the electrons towards itself and becomes negatively charged. So the positively charged species becomes the species which has carbon in it. The adjacent carbon becomes positively charged. So CH3, in CH3, the carbon of CH3 becomes positively charged. So the methyl group, that becomes this is just as this was chloronium ion, this would be methylanium ion, and this becomes the electrophile. And AlCl3 again gets converted into AlCl4 negative. The same thing happens in the case of what? Acylation. Acylation is COCH3. So you use CH3, COCl is used. And again the bond between Cl and carbon, chlorine being far more electronegative, even more than oxygen. Chlorine will pull the electrons towards itself and form Cl negative. So you'll be left with CH3CO positive. So CH3CO positive is the acylinium ion. And this would be the electrophile because it is positively charged, and the negatively charged chlorine would again go to AlCl3, result in the formation of AlCl4 negative. So in these three reactions where we used AlCl3, AlCl3 acts as the Lewis acid. Since it is a Lewis acid, it pulls the electrons towards itself, thereby making the remaining species of the other reagent positively charged. And therefore that other reagent becomes the electrophile. In the case of nitration, what we do, in the case of nitration, we use the nitrating mixture. And what is nitrating mixture? Nitrating mixture is a mixture of nitric acid and sulfuric acid, right? Now, look at the reaction. This reaction also takes place in two steps. The generation of electrophile here would be in two steps. In the first step, you have sulfuric acid here, which has been, we've written sulfuric acid as OH, it has an OH, sulfur to which OH has been added, and O3H. So HO3SOH. It's just a manner of writing it to show that this is the bond that would be breaking. The OH bond, that is where the breaking of the bond, the cleavage, asymmetrical cleavage will take place. Out of oxygen and hydrogen, which is more electronegative? Oxygen is more electronegative. Since oxygen is more electronegative, it will pull the electrons of the covalent bond towards itself, thereby releasing hydrogen as positive. That is what all acids do. Acids are those substances which are proton donors or electron pair acceptors. In this case, sulfuric acid is losing the proton. How? By asymmetrical cleavage, hydrogen being more electropositive and oxygen being more electronegative, the cleavage takes place, results in the generation of H positive. But now, the other region that you have is nitric acid, because we call it the nitrating mixture. Nitric acid in this reaction acts as a base, because it is nitric acid which accepts that proton. And by definition, anything that accepts a proton should be a base, and anything that donates a proton should be an acid. So what do you understand from this? Just by looking at this reaction, you can get an idea that sulfuric acid is a stronger acid than nitric acid. Because if you have the two of them together, acidity or basicity is only a comparative value, you know. It's only a comparative power. I am more powerful or you are less powerful. Who is, even someone who is slightly lesser powerful than me, I will win in a tug of war or in a wrestling match. So we say that nitric acid in comparison to sulfuric acid is weaker. Therefore, when you make the two of them react together, sulfuric acid acts as an acid and therefore it donates the proton, while nitric acid has to accept that proton and therefore it acts as a base. So when nitric acid accepts the proton, what is nitric acid? Again, it has an OH and NO2, HNO3, HNO3. One oxygen is written here to make you understand that this is how the bonds work. Now, when HSO3, out of H2SO4, H is removed, the HSO3 becomes negatively charged. HSO4 becomes negatively charged, and the HNO3 adds on one hydrogen, the proton adds on to it. And when this proton comes and it adds itself to this, it is positively charged. It uses, do you see these two lone pairs of electrons on oxygen? One of the lone pairs of electrons is used to form the bond. But hydrogen is positively charged, therefore this positive charge comes over oxygen. When this comes over oxygen, this is not a very stable species and it has still not generated the electrophile. For the generation of electrophile, you need to remove this water molecule from here. For the nitration to occur, you need to remove the water molecule. So in the next step, cleavage occurs, and the cleavage occurs in such a way that the bond between oxygen and nitrogen, it loses the electron to discharge the positive charge, to remove the positive charge, and therefore this positive charge now comes to nitrogen, because again an asymmetrical cleavage is occurring. We are separating out water, neutral water, and the positive charge now moves to nitrogen, because nitrogen gave its electron also to oxygen. Therefore now NO2 becomes positively charged, and this is known as the nitronium ion, and this is used for nitration, right? So what did we do for alkylation, for acylation, and for methylation? We used AlCl3, which acted as a Lewis acid and therefore acted as an electron pair acceptor and resulted in the generation of an electrophile. In the case of nitration, what we did was we used a mixture of nitrating mixture, a mixture of sulfuric acid and nitric acid, where sulfuric acid acted as an acid and nitric acid acted as a base, accepted a proton, and then water molecule was removed, leaving the remaining nitronium ion. In the case of sulfonation now, what happens? You have sulfuric acid and you have SO3. I told you we use oleum, that is concentrated and heated up sulfuric acid. That generates some sulfur trioxide, SO3. Now sulfur trioxide, sulfur has 6 electrons and each oxygen, SO3. Each of the oxygens has 2 lone pairs. Each oxygen and sulfur. Oxygen and sulfur each have 6 electrons in their outermost shells. And oxygen needs to form 2 bonds. So each, with sulfur, there are 6 bonds formed. In the case of sulfur, it is an expanded octet, but SO3 is formed. Now when SO3 reacts, the same thing happens. The cleavage in comparison to SO3, H2SO4 is more acidic. Therefore, asymmetrical cleavage will take place. A proton will be produced, and when a proton is produced, HSO4 negative is formed, but this proton will come and it'll come and attack the SO3, and it will attach itself to the SO3. When it attaches itself to the SO3, it does not come and attack sulfur. It comes and attaches itself to the oxygen. And one of the lone pairs is now used to form the bond. So when one of the lone pairs is used, what do you get? You will get SO, you still have the 4 bonds. This oxygen also has the 4 electrons, but this oxygen, O, uses 1 lone pair. Uses 1 lone pair to form a bond with hydrogen. Thereby, the positive charge now comes on this oxygen. And this is known as the sulfonium ion, right? And so we know how electrophile is generated in the case of chlorination, alkylation, acylation, nitration, and sulfonation. That was the first step, generation of electrophile, that is the generation of the positively charged species. After the positively charged species is produced, the second step comes, that is formation of a carbocation. Now this positively charged species comes and attaches itself to the benzene ring. And when it attaches itself, it is only adding on to the benzene ring. It transfers that positive charge to the ring, and that positive charge now starts rotating, or it becomes delocalized and it moves inside the benzene ring. Why? Because benzene ring has delocalized electrons, and these delocalized electrons, they help the positive charge to shuffle or to jump from one position to the other, resulting in these resonance structures. So let us see what happens. This was the benzene ring. Even if it was chlorine, as in the case of chlorobenzene, we'll have the electrophile either at the ortho position or the para position. but let us ignore that. Let us straight away take the benzene ring and see what happens there. You know why would we have orthopara, since the chlorine or the halogen is orthopara directing, why would we have ortho and para species, and why the para would be the major product? I've already explained that to you in the previous video. So let us just understand what electrophilic substitution is like. So the electrophile now attacks the benzene ring and if it is a haloalkane, it would be at the ortho or the para position. So let us assume that it comes and attacks here. When it does, now this carbon, it had a double bond here. So this double bond breaks, that is, these two electrons will break, and the two electrons of the pi electrons will be used up to form a bond with the electrophile. So this would, both the electrons are being given by this carbon, and actually one of the electrons is of this carbon. So as a result, what happens? This carbon loses that electron, it's a pi electron, and therefore the positive charge comes on this electron. As soon as the positive charge comes on this electron, the adjacent double bond, the pi electrons of the adjacent double bond, they start helping out. They say, okay, you're positively charged, we'll help you. We are free to, we are negatively charged, so we'll come and neutralize you. So these pi electrons, they shift to this side, result in the formation of a bond here, but one of the electrons of this bond belongs to this carbon. Therefore, the positive charge now shifts to this carbon. And a second bond is formed here. And now the same thing happens. The adjacent, it starts looking further. If there are more electrons available, the pi electrons present here say, okay, we'll come and remove the charge. So they shift, and this carbon now becomes deficient in electrons. Therefore, the positive charge shifts here. When that happens, again, you find the positive charge shifting here, and in the next you see that this double bond, again, if you go back, the positive charge comes here, so this bond again wants to provide the electrons to it, and therefore the positive charge will move back to the electrophile in the next step. So we find that delocalization occurs and positive charge starts moving around the benzene ring due to the movement of electrons which are delocalized, and result in the formation of this carbocation. This carbocation is known as the rhenium ion. It is also known as the sigma complex. It is only an intermediate stage. It is not the final product yet. So it is known as the rhenium ion. It is also known as sigma complex. You need to memorize this. And what is important to remember about the sigma complex is that the carbon to which the electrophile attaches itself, that carbon has 4 single bonds. Since it has 4 single bonds, if it had even one double bond, it would have been an sp2 hybridized carbon. But when you have 4 separate bonds on carbon, it means the hybridization of that carbon is sp3. So this carbon which has the electrophile, or in the rhenium ion where the electrophile is attached, that carbon is sp3 hybridized. So these are 3 things that you need to remember. First, the rhenium ion or the carbocation is also known as rhenium ion. It is also called the sigma complex, and the carbon to which the electrophile attaches itself is sp3, becomes sp3 hybridized. The moment sp3 hybridization comes in, the electrons now which were delocalized and which were revolving around the entire benzene ring, and also it is positively charged. That is not a very stable state. So what would the next step be? The next step would be to remove the positive charge. So how can you remove the positive charge? By the loss of this hydrogen. If the electrophile takes the place of this hydrogen and the hydrogen leaves along with the positive charge, which means how does anything leave with the positive charge? By leaving its electrons behind. When it leaves its electron behind, it moves out positively charged. So it takes along with it the positive charge. So from the rhenium ion, the next step is the removal of the proton. The proton is removed, and how is proton removed? In the form of H positive, and H positive will go and this H positive would react further with AlCl4. In each of these, when you got the positively charged ion, that is when you got the electrophile, you got a negatively charged species too. That negatively charged species accepts the proton. and when it accepts the proton, it results in the formation of the electrophilic substituted product of benzene. So when proton leaves here, with AlCl4, it resulted in the form one of the chlorines combined with H positive combined with Cl negative to form HCl, and AlCl3 was regenerated. And that is why we say that this reaction takes place in the presence of AlCl3, which means that AlCl3 only acts as a catalyst. It participates in the reaction and it moves out in the end. So AlCl3 is regenerated. Similarly, in the case of sulfonation, we see HSO4 negative, and both in sulfonation and in nitration, HSO4 negative are formed, and that accepts the H, and H2SO4 is regenerated. So these were the 3 steps of electrophilic substitution reaction. And with that, I'll finish this video. Now there are very small, just 2 reactions, Wurtz-Fittig reaction and Fittig reaction. So I'll be doing a very short video on that, and then we'll do the in-text questions and finally come to the last topic of the chapter, that is polyhalogen compounds. With this, I would like to wrap up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.